Hi, everyone. So today we're going to be looking at a preview of calculus. So this has been a course in pre-calculus, and basically what we've done this semester is try to solidify the skills that you're going to need in calculus. You're going to have to be good at trigonometry. You're going to have to be good at exponential functions. You're going to have to be good at algebra, maybe some systems of equations. But we haven't actually done any calculus this semester. So this lesson is going to give you just a little bit of a preview and maybe a tiny little head start on some of the things you'll see at the beginning of a calculus course. All right, so let's go ahead and get started. All right, so we're going to begin this discussion by talking a little bit about slope. And you know how to calculate the slope of a straight line. So I'll just say recall, we use slope to measure the steepness of a straight line. And when I say a straight line, I just mean a linear function. It could be horizontal, it could be diagonal, right? But it's sort of, how steep is it? Is it going uphill at a very fast rate, or is it going downhill, or is it kind of horizontal? For example, here's a couple of linear functions. Just a couple of quick ones. So this would be y equals 2x minus 1. That's what a slope of 2 looks like. And let's say this is a graph of y equals 1/3 x plus 1. That's what a slope of 1/3 looks like. So slope of 2, slope of 1/3. And I think that the larger the slope is, I would say the steeper the incline, right? And it's sort of like the one that has a slope of 1/3 looks like a hill that you could walk up, but the one that has a slope of 2, that looks like a mountain that would be hard to climb. So the larger the slope, the steeper the line is. Now that's not calculus, but here's a question that will kind of lead us towards calculus. How can we measure the steepness of a curved line? Yeah, the steepness of a curved line. We can't really do the same thing as slope, right? We need something similar to slope. So suppose we're looking at the graph of f of x equals x squared. We'll just use that as our example today because it's a simple function, but it's actually a really good function for this type of example. You know what that looks like. It's just the classic parabola that passes through the origin. You know some other points that it passes through. Passes through the point 1, 1, 2, 4, -1, 1, -2, 4. And it's a parabola that opens upward. Does it even make sense to talk about how steep this curved line is? It feels like with the linear functions above, there's sort of the same steepness throughout the entire thing, right? Like the slope of this line up above is 2 no matter where you look. If I look at it down here, it's increasing with a slope of 2. If I look over here, it's going upward with a slope of 2. But the curved line seems like if we were to do something like slope or measure how steep the curve is, it kind of depends what part of the curve we look at. At some parts of this curve, it's going downward. At some parts of this curve, it's going upward. So let's say that the steepness depends on which part of the curve we look at. So whatever we come up with that's going to be kind of like slope, it needs to take this into account. So maybe we focus in on a specific point of interest. How about we ask this question more specifically? So instead of saying, how can we measure the steepness of a curved line, let's focus in on what is the steepness at the point 1, 1. I'm choosing a point of interest and saying, let's focus in on what is happening to the function right around here. I'll label it 1, 1. And we could talk about, is the function, increasing rapidly? Is it decreasing? Is it, something sort of like slope for this curve? All right, so how are we going to do this? We answer this by looking at the tangent line. Now I have to tell you what that means. The tangent line at this point. So, this is a curved line. It's not straight. If this were a straight line, then we'd be able to calculate the slope. We know how to do slope of straight lines. So what we do is we draw a straight line at our point of interest, and it needs to follow the same steepness as the curve. So imagine, maybe we could zoom in on this for just a moment. Imagine a line that is straight, but at this point, it sort of follows the same direction as the black curved line. I think that would look something like this. I'm ignoring the rest of the curve. I'm just looking at what's happening to the curve right around here. And right around here, I think it's following this kind of direction. This tangent line that I drew in blue, I'll write tangent line next to it. It is a linear function. It's a straight line. It has a slope. And it just sort of grazes the curve at that one point, because that's the point that we chose to focus in on. So now we're turning this question into, what is the slope of the tangent line at that point 1, 1? So we keep rephrasing the question. I wanted to measure the steepness of a curved line. I said we have to focus in on a specific point. I chose a point to focus in on, and then I said we're going to do this by trying to figure out the slope of this blue line. And if we can figure out the slope, maybe it's something like 2, or maybe it's something like 3. If we can figure out the slope, then we'll say that that's how steep the curve is at the point 1, 1. Seems reasonable, right? Well, here's the issue, though. In order to answer this question, what's the slope of this line, we need 2 points to find slope, right? But we only have 1. 1, 1. The formula for calculating the slope of a straight line uses 2 points, so we need to do something about this. So here's an idea. If we need 2 points to calculate slope, then let's try to pick a second point nearby on the curve. I mean, I guess you could say that technically we would really like to pick a second point on the tangent line, but we don't know the equation of the tangent line, so we don't really know any other points that are guaranteed to be on it other than 1, 1. But we do know a bunch of points that are on the curve. So let's try the point 2, 4. And we could calculate the slope between this first point and this second point, 1 comma 1 and 2 comma 4. What is the slope there? Well, you would do 4 minus 1 over 2 minus 1. You'd get 3. But I guess you could say that that's not really the slope of the tangent line. I'll write that, not really the slope of the tangent line. It's close, though. It's kind of in the right general direction. Looking back at our picture, I guess it would be the slope of the line connecting 1, 1 to 2, 4. So we could imagine that going here. Like that. I just drew it as kind of a dashed line. And it doesn't exactly line up with the tangent line. It doesn't exactly have the same slope. So maybe this 3 that we found looks like it's probably a little bit too big. Like that slope seems a little steeper than the actual tangent line. By the way, this dashed line that I just drew, it has a different name. It's called a secant line. But the important thing is that we're trying to figure out the slope of the tangent line. Well, you might say that the point that I chose, 2 comma 4, is kind of far away from 1 comma 1. I used the word nearby, but is it really nearby? It seems kind of far. So how about we try a closer second point? So I have to move the picture away, but let's try a closer second point on the curve, because the curve is what we definitely can find points on. So how about the point 1.5 comma... Do we know a point on this f of x equals x squared that has an x coordinate of 1.5? Yeah, just whatever y coordinate goes here is going to be 1.5 squared, you know? F of x equals x squared. So this turns out to be 2.25. And if we calculate the slope of the line connecting these 2 points, 1 comma 1 and 1.5 comma 2.25, you get 2.25 minus 1 over 1.5 minus 1. This is 1.25 over 0.5. Which simplifies to 2.5. Now, remember a minute ago when we were looking at the 3 that we found and we were looking at the picture, and I said the 3 seemed like it was a little bit too big, that the actual slope of the tangent line was probably a little smaller. So I'm going to say the 2.5 that we got, I think, is better. But it still might not be exactly the slope of the tangent line. So here's what we're going to do next. What if we tried a second point that's even closer? And I have a little table to show you. I've already calculated these. Remember that our first point of interest was 1 comma 1. We need a second point in order to calculate slope. So here's a little table of some points that I tried. Well, we already talked about 2 comma 4. We found a slope of 3. We talked about 1.5 comma 2.25, and we found a slope of 2.5. I decided to check some points that are even closer to 1 comma 1. So one way that you could do that is 1.1 comma 1.1 squared. That's a point that's on the curve, and it's really close to 1 comma 1. How do I know it's on the curve? Well, this is x, and why am I squaring this? It's because the function says f of x equals x squared, so that's why it's squared. If you do this and you calculate the slope, you get 2.1. I also checked a point that's even closer, 1.01, 1.01 squared. And this, with the slope formula, gets us 2.01. And I did one more. I did 1.0001 comma 1.0001 squared. Can you imagine on our picture how close this is to 1 comma 1? We're finding the slope of a line between 2 points that are so extremely close to each other. All right, I'm just going to show you the picture one more time. 1.0001 comma that y coordinate, that's right next to this. Like on the picture, they'd be indistinguishable from each other. The 2 points are almost the same point. And because of that, it's like we're zoomed in extremely close, and that's going to tell us the behavior just in this area. And that's kind of what we want. So it turns out that the slope that we would get is 2.0001. This seems very close to 2. This seems very, very, very close to 2. The closer my second point gets to the first point, it seems like the closer m gets to 2. So how about this? How about this? Let's remember that our first point was 1 comma 1. What if we let the second point be x comma f of x? I mean, I'm trying to be more general here. We have a table that seems to suggest that the actual slope that we're looking for might be 2. I think the slope we're trying to find here might be 2. These were specific values. Now I want to look generally. I guess this x comma f of x could be thought of as x comma x squared, because the function is f of x equals x squared. The slope of the line through these 2 points is, when I say these 2 points, I'm going to underline them, the point 1 comma 1 and the point x comma f of x. We would get x squared minus 1 over x minus 1. As x approaches 1 in the table above, we let the x-coordinate get closer and closer and closer to 1, right? We started with 2, then 1.5, 1.1. It got closer and closer to 1. And as that happened, we find m approaches 2. The answer that we got became closer and closer to 2. We say the limit, I'm going to underline that, we say the limit of x squared minus 1 over x minus 1 as x approaches 1 is 2. So let's look at this sentence carefully. This is a piece of terminology that you'll see when you take calculus called limit, and you'll have an actual official definition for the word limit. Right now, we're giving kind of a preview of calculus, so being a little bit less formal. I'm not stating the formal definition of limit, but this is an example of one. We say that this expression, which is the formula for slope here, as x approaches 1, we say the limit of this is 2, because the answer that we got was getting closer and closer to 2. We can write this as, so the sentence that I just wrote here in words, we have a way of abbreviating it. We say lim x with an arrow pointing to 1 of this expression equals 2. And this is called limit notation. We say the limit of x squared minus 1 over x minus 1 as x approaches 1 is 2. So the x with an arrow pointing to 1 means x is getting closer and closer to 1, as it did in our table above. In fact, it got incredibly close to 1, 1.0001. Maybe we could let it get even closer, add some more digits and get even closer, right? The closer x gets to 1, the closer this expression gets to 2. And that's what this notation means. Now, in an actual calculus class, you're probably not going to rely on making a table every time you want to investigate one of these things. And it turns out that we could get this. We could get this answer without the table. You know, in math, a table of values is usually something that you, I don't know. I guess when we first learn about how to graph functions, sometimes we use a table of values, and then we learn more sophisticated ways of graphing things. So we try to get away from using a table. And right now, I was using a table to try to talk about this concept of a limit, but it turns out that we can do this without the table. So this expression that I wrote above, I'm telling you based on the table, I think this answer is approaching 2. Well, we could actually do a little bit of algebra on this, and I see that the numerator can be factored to x plus 1, x minus 1. So this is useful because now I have an x minus 1 over x minus 1, and we can cancel them out. So I'm going to cross out x minus 1 and x minus 1. What does that leave me with? Just the limit as x approaches 1 of x plus 1. Now, we've kind of simplified it, and what this last expression is saying is, what is the limit of the expression x plus 1 as x approaches 1? Well, if x approaches 1, this thing in parentheses is just going to become 1 plus 1. And the answer is 2. So yes, the slope of the tangent line for that particular curve at the point of interest 1, 1 is exactly 2. Now, note that there's nothing particularly special about the point 1, 1. I just chose it as an example. We could use this same idea to investigate the slope of the tangent line at other points on this curve or on other curves defined by other functions, right? So this was a lot of discussion about this parabola and this particular point. But really, it's the overall concept of we have a curved line and we found a way to measure how steep that curve is at a particular point. So in general, let's step away from the parabola example and let's just be more general. The slope of the tangent line through the point a comma f of a is, this is basically the 1, 1 that we were using. So I'm, trying to be more general, so I'm not writing 1, 1, but that's basically what it was in that example. It is, well, we usually call slope by the letter m, so it turned out that it was the limit as x approaches a of f of x minus f of a over x minus a. This is basically how we got that kind of x squared minus 1 and x minus 1. Okay? By the way, this sometimes might not exist. You know how the slope of a vertical line does not exist? So I'm talking about this slope kind of assuming that it does exist. I have two big ideas to tell you. Big idea number one. First of all, if we define the number h to be h equals x minus a, then we can rewrite the formula as the limit, instead of x going to a, if I introduced this letter h, when x goes to a, x and a are approaching the same thing. They're practically becoming the same number. So h is going to become 0. So we could actually rewrite this as a limit as h goes to 0. How does that change the rest of this? Instead of f of x minus f of a, I'm going to write it as f of a plus h minus f of a, all of that over h. So these are two different formulas, but they're describing the same thing. Maybe you say that the second formula, it looks like the numerator is a little bit more complicated, but the denominator is a little bit simpler. So maybe they're about the same in terms of how simple or complicated they are. Big idea number two. M is a function of a. What I mean by this is that m only depends on a. We've been saying that the slope of the tangent line, which sort of measures how steep the curve is, it depends on what part of the curve you look at. Well, what part of the curve are we looking at? We're looking at this point, a comma f of a. And depending on what we put in for a, we might get a different m. You know, if I put in a equals 1, I might get one thing. If I put in a equals 2, I might get something else. If I put in a equals 3, I get something else. We're describing a function. The slope is a function of a. So we could say, instead of m, we could call it a function of a, like m of a, right? And we could write the limit as h goes to 0 of ... all that stuff above. We could write it that way, m of a. And you plug in a certain input, like a certain value of a, and then this formula gives you the slope. But instead of calling it m of a, we call it f with a little symbol up here of a. And this is pronounced f prime of a. It's just a different way we write it. You know, we're used to thinking of slope as being represented by the letter m. But because this is a function of a, and we like to refer to functions with the letter f, we're going to call this f prime. So the idea is that you have some function f of x, and you want to know maybe the slope of the tangent line at a particular value, x equals a. We call it f prime of a. And this leads us to a big definition. I don't think I've stated any like formal definitions in this lesson so far, but we should at least have this one. The derivative. The derivative of a function f of x at a number a denoted by f prime of a is f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a, all of that over h. And I'll say if this limit exists. I mentioned earlier that sometimes slope does not exist. So this is the definition of the derivative of a function at a number a. It's the same thing we've been talking about for the past few minutes here. I'm just giving it a name. We gave it two names, I guess. First we called it f prime of a, and now we're calling it the derivative of f at a. So the derivative seems like it tells us the slope of the tangent line at a particular x value, right? This number a that we're putting in, don't forget that a is basically an x value. How do I know that a is an x value? Watch this. It's right here. This is where a started. A started here as basically an x value, right? X comma y is what we do for points. So a is a particular x value that we're interested in. And at that particular x value, you can find the slope of the tangent line. All right, so let me sort of summarize this, or tell you the main idea, the key idea. The derivative tells us the slope of the tangent line at a, so it's a way of measuring the steepness of the curve at that point, at that point of interest. All right, so when you take calculus, I mean, right now, this is a pre-calculus class, so we're trying to prepare you for calculus, and when you take calculus, you'll talk about the derivative in more detail, and you'll talk about limits in more detail. I'm kind of summarizing a bunch of things into this one lesson, but this is the main idea. We use this thing called the derivative. It's often written as f prime, and it's for measuring the steepness of a curved line at a point of interest. By the way, you might have noticed that this expression might look a little familiar to you. I don't know, have you ever seen something like f of a plus h minus f of a over h? Or maybe you've seen it with like other letters, but something that kind of looks like this. It's a quantity that's sometimes called the difference quotient. It sometimes shows up in algebra classes. The part f of a plus h minus f of a over h. It shows up in the formula for the derivative. But I know that I've seen this expression show up in algebra classes before. Just in an algebra class, you might be given a function f, and it might ask you to, calculate or simplify this expression. If you've ever seen that before in an algebra class, the reason why it's sometimes included is to prepare you for this moment. It's to prepare you for calculus. This type of expression doesn't really have much use on its own, but it does have uses when you put it into that derivative formula. So in calculus, you might have to simplify expressions that look like this because you're working on derivatives. Now, what does the derivative do for us? Let's think. We know that it does slope of the tangent line. It's kind of telling us how steep is the curve. I guess you could say it could tell you if a curve is going upward or downward, because if the slope is positive, it's going upward. If the slope is negative, it's going downward. Let me tell you some applications. Just of the derivative, I guess. Like the derivative of a function. So first, I'll just say slope is a rate of change. Because slope can be thought of as the change in y over the change in x. Or it can be thought of as the change in f of x over the change in x. Notice that the derivative formula and the difference quotient, they basically look like this, right? The numerator is the change in f, the denominator is the change in x. We say that the derivative measures the instantaneous rate of change. It's sort of how much is the function changing at that particular moment or at that particular point? Well, there are lots of real-life rates of change that we might be interested in. How about velocity? Velocity is a rate of change. It's often thought of as the change in distance over the change in time. So if we had a function f of x that was measuring distance, maybe we could use the derivative to help us figure out velocity. For example, it might be measured in miles per hour, or it might be measured in some other units. But yeah, velocity, how fast something is going, can be thought of as how fast is a function changing. There's also applications to other areas like business, such as a rate of change in total sales over a change in time. And that might be measured in something like dollars per month. So maybe you want to know at what rate is the total sales changing? At what rate of change is that? These are just two examples, but there are many applications. Depending on what your major is, you might see them in other classes. Applications of the derivative show up in science, technology, business, architecture, and more. And, when I say science, that includes biology, physics, chemistry, computer science. Pretty much any science you could think of is going to use calculus in one way or another. So far today, what have we done? This has been a preview of calculus, and we spent most of the time discussing this concept that ultimately became what we call the derivative. We were trying to measure the steepness of a curved line. We wound up eventually calling it f prime of a, which I said is called the derivative of the function. And it's showing us a way to measure the rate of change or the slope of something that is possibly a curved line. And we did this on f of x equals x squared, but you could imagine that the overall principle applies to any curved line. So let me tell you some other things that calculus studies. Because if this is a preview of calculus, I want to leave off by telling you a few other things, not just the derivative. All right, so yes, rates of change. Also known as slope, also known as derivatives. Part of what you'll do in a calculus course, you'll start off a calculus course by learning a lot about limits. And you'll learn how to evaluate limits, and more than what we did today, you'll learn an official definition for limit, and then you'll get into talking about slope and derivatives. And you'll spend a lot of the course learning how to calculate derivatives of different types of functions. You'll see some applications to objects in motion. Objects in motion, I'm talking about concepts like distance, velocity, acceleration. This is where some applications to physics show up. You know, an object is dropped from a great height. How fast is it moving when it hits the ground? I don't know, a cannonball is launched into the air, maybe like a projectile motion. What is the acceleration of the object? Lots of things like that. Calculus looks at what happens to a function when x approaches some number. I used the word approaches earlier today. This is really the concept of limits. You'll talk about that in more detail in a calculus class. Another thing that calculus studies that I haven't talked about yet today is infinity. What happens to a function f of x when x approaches infinity? This is actually just kind of a different type of limit. Instead of x approaching some number, x is approaching infinity. Infinity is not really a number. It's not like x could never actually equal infinity, but x could get really, x could approach it. The idea of x approaching infinity is the idea that x is growing larger and larger and larger forever. What's happening to the function as that happens? Does f of x also become infinity? Well, it might or it might not. Another thing calculus studies is what is the area of a curved region. Yeah, area shows up. So a curved region, I was just going over this with my calculus classes, but let's say you have, here's the x-axis, y-axis. Maybe you have some kind of function. All right, you've got some kind of function here, and you want to know, like, maybe what is the area of this region? Can we figure out the area of this? I mean, we know how to do the area of a rectangle or the area of a triangle or the area of a circle, but what about a weird shape like this? So it looks like the left side of it is flat, the bottom is flat, the right side of it is flat, but the top is curved, and that's what makes it an interesting question. So calculus shows you how to answer that. Another thing calculus looks at is what is the volume of a curved three-dimensional shape. So maybe an example of that would be something like a, I don't know, like a cone or a funnel. It's kind of hard to draw three-dimensional pictures, but you can imagine that this is a three-dimensional object, maybe like a traffic cone or something with a little bit of a curve to it, though. Can we figure out the volume of this? Well, I guess when it comes to volume of three-dimensional shapes, we probably know how to find the volume of a box. Maybe we've seen, at some point in our lives, maybe we've seen like a formula for the volume of a sphere or the volume of a cylinder. But what about other weird shapes like this? That's another thing that calculus can answer. How about what is the length of a curve? So this is also something I can just draw a quick sketch. What if you had a curved line from one point to another? How long is that curve? I mean, if it was physically in real life, would you try to measure it with a piece of string or something like that? But mathematically, how can we get the exact length? That's something that calculus can do for you. How about this? If you're given y equals f of x, what is the largest y value? What is the largest y value that this function has? So this might be a curve that maybe, depending on the function, maybe it kind of like goes up and down. All right, y equals f of x. And maybe there's some point that is the largest y value that this function ever achieves. It never goes any higher than that. The top of the mountain. This actually turns out to have a lot of useful applications because in real life, sometimes you want to know what is the largest that something can be. Depending on what the function represents, sometimes this is telling you the best way to do something. Like, for example, I want to manufacture, I don't know, I want to manufacture like a container, like a can, like a metal can that's going to hold vegetables. And I want it to contain the maximum amount of possible volume, given some kind of restraints, like I have a certain amount of material available to me or something like that. So sometimes this type of question shows up when you're trying to find the optimal way to do something. Or maybe it's a business question and you're trying to find the maximum profit. You know, maybe the function represents profit. You want to find the maximum profit. Or you could also flip this question upside down and say, what is the smallest y value that a function has? Maybe there's something that you're trying to do in the minimum amount of time or the minimum amount of distance. So this actually turns out to be a pretty useful question. Calculus helps you answer this. In fact, derivatives help you answer this. All right, so this has been kind of I guess, a quick summary of some topics that calculus gets into. I'll just say, and more. Some of the things that I covered here are in Calculus 1. A couple of them are actually in Calculus 2. I think the volume of a 3D shape, that's more of a Calculus 2 question. The length of a curve, that might be a Calculus 2 question. The rest of them are Calculus 1. All right, so let's wrap things up here. All right, so this lesson has been a preview of calculus. We are basically at the end of pre-calculus now, and I wanted to give you this little sneak peek, maybe a tiny little head start on what calculus is, so that when you take Calculus 1, you already have some idea of some things it's going to cover. It's hard to summarize calculus into one lesson, and, can you walk away from this lesson understanding what calculus is? Probably not. I mean, really, to understand what calculus is, you really need to take a full semester of it. I'll tell you that it's hard to even come up with a specific definition of calculus, even if you ask a student who has taken calculus before, what is calculus? I'd be interested to know what they say. I've seen some textbooks say that calculus is the study of how things change. The study of how things change. And I kind of agree with that definition, but on the other hand, I kind of think calculus is much more than that. I think it's the study of how things change. It's also the study of limits and derivatives and infinity, and also some concepts we didn't talk about today, like continuity and integrals and volume. So calculus is a lot of things, and you'll take a full semester of it to really get the big picture of what it's all about. But anyway, hopefully this one lesson was interesting and you saw a little sneak peek. So that's it for today, and everybody take care.